Okay, yeah, welcome everybody. And I'm going to speak about the graph tables with you today. And I just want to say thank you all the sponsors first. We couldn't do this without them. And thank you all the organizers and volunteers too. I know it's not easy to, make this happen. It's a lot of work, and we appreciate for that. Today, I am going to speak about graph tables in SQL Server. Graph tables are introduced to SQL Server in 2017 version, and there are a couple of updates came up in 2019. So I'm going to try to explain you first what the graph tables are and who's using them. Then we can go in details, and I will kind of show you how to create them, how to update them, and there's like some tips you should know. And we will end the session with a demo. So I will show you how to do that actually in practice. So that is the plan for today. And before I go in details, let me speak about myself. My name is Hasan Savran, and I am a business intelligence manager in an insurance company in the United States. I'm from Cleveland, Ohio, and I'm a Microsoft Data Platform MVP. This is my second year, and I am proud and very happy about it. I have been doing web development for 15 years, and almost 8 years I'm in the business intelligence kind of business in the insurance company. You can actually follow me in any of the platforms you see on the screen. I'm pretty active, especially in Twitter and LinkedIn. I try to share whatever I know. Usually those are Cosmos DB, SQL Server, front end, and C#. And I try to write at least 2-3 times a month in my blog. Check it out, my blog. You might see something interesting up there. And most of the stuff I'm going to cover today, you can see more details and quotes in my blog out there too. So let's jump in to our presentation. We live in a connected world. In this connected world, things change quickly. If we give some examples like that from the recent times, for example, think about the evolution in the entertainment, right? We used to actually go and rent the movies. Now that business is gone. Or if they were smart, they do something about it and actually they move to digital platform. We can give another example for evolution in the cars. So the cars, some of the cars are actually can drive themselves. So that's kind of like a big change for all the businesses who's actually selling the cars and insuring the cars. How are you going to insure those cars? Or the selling is going to be changing. So there's a lot of changes going on out there. Evolution in the IoT. IoT business right now, I think in 2020, we supposed to have like 50.1 billion IoT devices on Earth. And that brings a lot of opportunity for everybody, and that brings a lot of data. So we kind of need to handle that data, analyze that data, store that data. Evolution in healthcare. That's a kind of tricky one. Everything, all the doctors were used to, in the United States at least, was, charting everything on paper, right? And like 7 or 10 years ago, things start to change and everybody started to move to digital platform. And that was a big, big change for the doctors, for the nurses, and for IT. And we have like really important data out there we kind of need to handle. And those changes happened and new ones are happening. So creating data models for any kind of business is getting more tricky because the changes comes up like that. They can be big changes like that or small changes. Because of that changes, you might need to create a new table or new relations between, other tables. And that sounds easy, but in the relational databases, that can be a challenge. Usually when you add a new table to your data model, that means you are going to have one or more joins, right? And usually joins are like the curves on this screen you see. So you might be going on the highway and you are going at 120 kilometers per hour. And when you try to go and merge to another highway, well, you kind of need to, I guess, slow down, right? Because the curve is you're not going to go in 120 in that curve. And depending what kind of curve or what kind of highway you are trying to join, you might really need to slow down. And that's really how the relational database tables joins work. And if you have many joins, usually that means your query is gonna work a little bit slower. And also in relational databases, you cannot create a many-to-many relationship directly between two tables. You almost need to create another junction table in the middle, and you need to join two tables so you can actually make the many-to-many relation. So those are kind of limits of the relational database. Relational databases do not adapt well to the changes. They work best for the problems when actually you have the problem right in front of you and it's well defined and you actually create the data model by looking at it. But when a change comes up, usually things can get really tricky. So whenever you are creating a data model right now, you really have to think about feature, what might actually change this data model rather than what you are trying to fix today's problem. Your data model should be open to the new domains, new relations for feature changes. Graph database tables actually gives you this flexibility. So that's why I kind of like them. Graph database tables, you can actually join them with the regular tables with no problem. So they will give you a lot of flexibility when it comes to especially the relations. Graph database tables are not new. They have been out there for some time. And as I said before, they are introduced to SQL Server in 2017. So the first question usually I get is like, who's using the graph tables? Well, I can give you three options. Well, those are probably the main options. The first one is just like a suggestion engines. What is suggestion engine? For example, when you go to the Amazon, right, and you are looking for a product, let's say if you want to learn about Kubernetes, right? And you are like, okay, I should go and buy a book about Kubernetes. So you go to Amazon, you go and look at all the books, and you find a good one. And you say that, okay, this sounds good. So you start to kind of scroll down on the screen, and you see the picture of it, you see some of the maybe reviews, you see the description from vendor, from writer, or whatever. But when you start to go scroll down more, some more interesting things comes up on your screen. Amazon actually starts to give you some suggestions and saying that, you know what, who's buying this product usually buy other products like this one, right? So that is not real, but you get the idea. That's just a joke out there. So to do that in relational database is a challenge because you kind of need to go in, like OLTP database and try to join who knows how many tables and actually suggest that dynamically for every product. That's a big, big query, I imagine. The best thing probably you can do here is you might maybe run an SSIS package, which actually does that for you every maybe 1 hour. And you go and look at that table whenever actual users are reaching that part. So that's maybe possible, but you need the SSIS package for that. So graph database tables are great actually to give your users a dynamic with suggestions like that. Second one is the government. The government has many agencies, and probably you have records in many of those agencies. So whenever somebody from one agency maybe write your ID, they want to see your name once. They don't want to see your name coming from each agency many times, because mostly your data is going to be the same. So it's going to be like kind of digging the data and try to find what they are looking for. So that's what you are looking for, a master data management database structure. So graph database tables are great for that solution too, if you are trying to create a system like that. Third one is the social media. The best example I can give you for that is Facebook. So what do you do when you go to Facebook? Usually you kind of like things, like you like post, you like picture, you like, whatever is out there, you like them. So if you think about it, really you are the user, which you are the entity, and there are some other entities out there like a photo, shop, post, whatever, those are other entities. And the relation between them, that whenever you click the like button, is always same. So you like photo, like picture, whatever. So graph tables give you really a special way, so you can actually create these relationships much better and much flexible. Everybody talks about the graph database tables. They kind of compare these two data types, which is good because graph database table is great for hierarchy data. So SQL Server has another data type named hierarchy ID, and that is introduced, I think, in 2008. So it has been out there for a long time. So if you compare the hierarchy ID to graph database tables here, the first thing you need to know is in hierarchy ID, everything is really structured, highly structured. So it's the best example I can give you is the HR system, right? Every company has this HR system. You have your CEO, and after that, people are reporting to that person, people are reporting to managers, whatever. So it's really highly structured. The changes are really minimal. And also the person can have many people can report to that person, but a manager cannot have more than one managers. For example, a company cannot have more than one CEO, right? So that kind of fits the hierarchy. In graph database tables, actually, they are more flexible. So a manager can have more managers, more than one managers, or a company can have more than CEO, for example, if you are going to try create this in the graph database tables. And both are indexable. And to find your data in hierarchy ID, you need to use one of those CLR functions since the data is getting saved as binary. And in graph database tables, you need to use the match clause in your where filter. As I said before, hierarchy ID has been out there, and I have been using it. Many people think that it's old and not useful, but I use that a lot in my job, actually. And the other big difference between them is hierarchy ID, as I said before, it can have only one root. And graph database table can have multiple, if you like. And that's why the many-to-many relation is actually really nice to have in graph database tables. So how does actually graph database table does this flexibility? Well, the first thing you need to know is there are two data types in graph database tables. And one of them is the node tables, which actually holds the entities. What are entities? User is an entity. Product is an entity. Warehouse is an entity, right? And in these node tables, there is one special column named node ID. And that's the identity of each entity. It's getting auto-populated every time you insert the data. You cannot update it, you cannot change it, you have absolutely no business with it, just leave it alone. But I'm just, you kind of need to know about it because to create any kind of relations between two entities, you're gonna need the node ID. And also the system is gonna use the node ID in the background whenever you are looking for data. So it's important that there is an index on the node ID. Also, in node tables, you can have any type of data types. Whatever SQL Server supports, you can create that in the node tables. Edge tables actually keeps the relations between the entities. So relationships are first-class citizens in graph database tables. Now, just like the node ID, just like the node tables, edge tables has a column named edge ID, and that's the identity of each relation. And just like the node ID, you absolutely have no business with it, just leave it alone. It's getting auto-populated. And as I said before, it's getting used by the system. So it's important to have an index on it. And very interesting fact of edge tables, they can have any type of columns. And that means you can put any type of data type SQL Server supports into that table. That actually gives you really flexibility. So you can, for example, if you are creating a relationship between two users and you are saying user A likes user B, you can have all type of metadata about that relation in that relation table. You can figure out when it happened, how it happened, why it happened. You can have all those columns there. And to make a relation between two entities, you are going to need two different type of columns, which is the from ID and to ID. Those two columns hold the node ID of the entities we are trying to make the relation. So let's say, for example, we are going to create a relation. We have username I, and we have another username Anna, right? So and we have an edge table named like. So what you are going to do here is you are going to take the node ID of Alec, and you're going to put that in the from ID, and you are going to take Anna's node ID, and you are going to put in the to ID. And that is going to make a relation between Alec and Anna, and that's going to be a like. So Alec likes Anna. Directions are important. So what I mean by that, so in our example, we said Alec likes Anna. That doesn't mean that Anna likes Alec better. To make that relation, you have to create another one, which is gonna be from ID is gonna be Anna, and Alec is gonna be to ID. So Anna like Alec back in that case. So directions are important. Relations cannot be updated. What do I mean by that is you cannot update from ID and to ID, just like one of those special IDs. Because probably you don't want to do that. So for example, our table is like table, right? There's only one case our table actually cares, if Alec likes Anna. If that changes, you just drop that relation. You can go and actually update other columns if you have, for example, if you have credit dates and how they meet and other stuff. For example, you can have those string or varchar columns. You can update them. You just cannot update from ID and to ID. Now, how do we create them? It's pretty easy. There's really not that much to learn here. So for example, in node tables, I am creating a products table, right? And everything is really same. I put all kind of data types in it. The only thing difference is, as you can see at the end, I have as node. That makes this table a node table. And nothing is actually changed here, as you can see. I don't even define the node ID because node ID is getting defined by whenever you create a node as node here. So you don't need to worry about that. So you just create a table by just saying as node, we are making this a node table. That works with the edge tables. Same way, I'm still using the create table syntax. If you want, you can add any kind of columns here. And by just saying as edge, this relation table is getting created. So as you can see, I have products table and a like product. So what I'm trying to do here is just like the example I gave you in Amazon, maybe I'm going to try to find the products like each other and like products, so I can give a list to my user dynamically. So when you actually create this, you are going to see then under the graph tables folder. This is from SSMS. And as you can see, I'm not sure if you can see, but there's a really icon, almost looks like the glasses on that table that tells you that this is a relation table. And if there's like a one solid dot, that shows you that this is an entity, which is a node table, and they will be under graph tables. What about creating data? As you can see, really there's nothing different here, especially in the node tables. You are still using the insert statement. You are just listing whatever data types you want to insert the data into, and you just pass the data. But there's absolutely nothing, I guess, changed in here when you try to insert data to node tables. Edge tables are a little bit different because you kind of need to tell which entities you are trying to, create this relation between. So in here, for example, we are saying I want to get the node ID of ID1, which I'm guessing that's going to be Kindle Fire 7. And I'm getting the product ID2, and I'm getting the node ID of that too, and that's the HD8. And since I was actually trying to track when I'm creating this data, so I'm just passing the current date here. So that's it's a data type or data column in the Alike product. But this one actually makes the relation between Kindle Fire 7 and Kindle Fire HD8. And I'm putting them in the Alike product. So there's a relation between them. When it comes to updating, you can update any columns rather than node ID, edge ID, from ID, and to ID. You can update any of the columns of node table on edge table, and you are still using the update statement to do that. And I'm going to cover that match clause in a little bit. And as I said before, you cannot update the relations. Now, whenever you are trying to select the data, if you are actually going to use just select all, you're going to be able to see the node ID, age ID, from ID, and to ID. Usually, whenever we are trying to actually return the data, probably you're not going to return those because they are kind of useless for the user. But as you can see, actually, when you write the select all, there is a JSON document in that. And for example, in here, this is the node ID. This is really telling you where this table is and what the ID is. And in the from ID, this one tells you these are the product, these are the ID, and what is getting removed. I have a relationship from going this entity to this entity. So you might, if you write the select all, whenever I run this first time, I was surprised that actually there were JSON documents. So I just want to share that with you. Now, when it comes actually try to find the data in graph database tables, you have to use the new match clause in your where filter. Match clause accepts graph search pattern. That one actually specifies the pattern, what you are trying to find in the graph database tables. This pattern has to start from one entity, it has to go to another entity, and it needs to use one relation between. So that is the minimum. You can use more than that, but you must have at least 2 entities and 1 relation. You are going to use the arrow character to specify the direction. Just like I gave you an example with Alec likes Anna doesn't mean that Anna likes Alec. The arrow is going to actually tell us which data we are trying to find. And you are going to probably have, if this is the minimum, you need 3 tables here, right? So it can get a little bit kind of, I guess, confusing when you write the query. And probably you're going to use arrays for those names of the tables. So we use a parenthesis, and that one tells you that the one, the alias is for a relationship table. It makes a little bit your life easy. So here's an example, a simple example. So it looks like we are using products table here, wish table, and users table. As you might guess, our products table is a node table. It's an entity. Users table is an entity, and wished is a relation table. So my match clause is actually starting from the users table, and it's going to the products table by using the wished relation. And as you can see, the direction is going this way. So by just writing that, I am going to find all users wish list. But I don't stop out there. I say end user ID 1. So I want to actually find user ID 1's wish list by running this. So that's what's going to actually do. As I said before, this can get more complex than that. You can add more logic here. You can have more tables out there, but that is the minimum. So you need two entities and 1 relation. Now, let's have some examples. The first example I'm going to give you is the Amazon example I have been talking about. So this is a great example, and if you have like any kind of application like Amazon, you might want to do that for users. So you can say that, okay, you are looking at this product, but guess what? There are some other products like that, and you might like it. So to do that, what I'm doing here is my entity is actually the same. I'm going from product table to the other product table. And I'm going to have a edge table for Airline. So what I'm going to do here is I'm going to have my products table. And in some way, you kind of need to figure out which product is like which product. And you're going to create all the data in your edge tables. Then you are going to be actually ready to write the query. And the query is going to be very simple. You are going to go from product table to product table by using the alike relationship. And let's say the Skimplifier's ID is 1. So this is going to give you all the products very easily. And you can just put that dynamically at the end of your page, just like Amazon. Second example, which is a very common example for healthcare, if you are in a digital area, is many patients come to hospital, right? So, but this patient doesn't just go to your hospital; it goes to many other hospitals. So maybe they go to the labs, they go to step cares or whatever. So this person has many records. And every time he goes to different, areas, they, register. And maybe this person's name is a Mike Miller, and we register him as a Michael Miller. But he got some lab results, and actually they registered as Michael T. Miller. because he has a middle name, and they kind of use the the short term for his name in Mike here. So you're going to have a system which is going to take all this data coming up from all those other sources, and you need to create some kind of business logic and actually match and merge this data. So whenever your doctor in your hospital actually opens this chart, he's going to be able to see everything, all the data from your hospital, other hospitals, and maybe other labs. So this is a kind of like a challenge process. It's not easy a process, but graph tables can actually do that very easily for you. And to do that, all we really have to do is now, rather than products, we are using our patient table. We are going patient to patient table. We are using the same relation. And as you can see, let's say we are looking Mike Miller as the ID1, and this is going to give me all the information that I need to know about this patient that might be other, coming up from other sources. The third example I have is, well, Facebook, right? So we go to Facebook and we see this bird and we say, wow, this is a nice bird. We click like. So when you click like, what's going to happen here is you're going to insert a relation between you, which is the user. You're going to find the user's node ID, and you're going to find the node ID of this picture or post, whichever. Then you're going to insert that in a like table. Now, from that point, you are ready if you want to actually list what I like. It's going to be very easy. As you can see, this time, my entities are not the same anymore. I'm going from users table to post table by using the like relation. And let's say my ID is 1. So this is going to give me everything that I like in the system. In 2019, we had some, I guess, as I said before, upgrades came to the graph database tables. And this is available in the Azure SQL 2. So if you look at this table or the structure, we have a user and we have a product. Both are entities, right? And let's say we have a wish kind of table in the middle of them. So we are kind of tracking wish list of user. In 2017, you can create the relation between user to product. Interestingly, you can create the same thing between product to user. So what I'm trying to say is user wishes product, but nothing is stopping product to wish user. So that can be a trouble. You might have some mistakes out there, and it's good to have some kind of constraint so we can control what entity can be connected to what other entity. In 2019, we got that. And to do that, here's how you do it. We are still using the alter table for that. We are adding a new constraint. We are giving a name, and we are saying the connections between can go from users to product. So this full stop. If you try to create a relation between product to users by using this relation. This can get more complex. This is only one relation. Actually, it accepts multiple. So in here, I'm saying is, okay, this wish can go from users to product or guests to product. You can actually have multiple if you like. Also, you can control what's going to happen if a delete happens. So if a delete happens to users or product, you're going to have a relation between something doesn't exist anymore. So in this case, by saying that, you are going to actually, the SQL Server, if you, for example, delete the user ID 1, then we are going to delete all the wished list of user ID. Or you can say that, okay, you know what, I don't want to delete it. I want to get no action. No action means, yes, when this happens, database actually engine raises an error when you try to delete the node. So you cannot delete it in this case. So those are pretty useful upgrades. Now, just like in the data types or data tables in SQL Server, indexing is important for the graph database tables. So you have this 4 special IDs: node ID, age ID, prom ID, and tool ID. You might not use them that much in your queries, but system uses them constantly to find data by looking at match clouds you write. So in here, for example, the Microsoft suggests that you should create indexes in node ID and age ID. The good part about this is if you forget doing that, actually SQL Server does it for you. but it doesn't do that for the from ID and to ID. So that's going to be your responsibility to create a unique non-cluster index on this. So let's look at this example here. What I'm going to show you first is I have absolutely no indexes. So I'm guessing the only index I have here is the node ID and edge ID. So I'm trying to find all the products here, just like the Kindle Fire 7. I'm finding the products like Kindle Fire 7. So it's pretty simple. If I run that and look at the execution plan, that's what you are going to actually see. Since I do not have any indexes, you see a table scan in elike product. So I am scanning the whole table to actually find this, and this is not good. The main reason for that is because I don't have an index in my elike table in the from ID and to ID. To create an index, really, it's just we are still using the same syntax to create the index. We are creating a unique non-cluster index. We are giving a name. Those are the tables, and those are the columns. So after I run that, and if I actually go and run the same thing, then we're going to see that table scan is gone, and I start to have actually index seek for the elike product. This is important because usually the relation tables can get really big. So it's important that you should have index on the from and to ID of each relation table you have. All right, the next update we get, the advanced one actually, is shortest path. And shortest path is kind of tricky when you look at the syntax of it. So what I'm trying to do here is you have two entities, and you are trying to find what is the shortest way actually I can reach from this entity to this entity. So we still use the magic codes, but as I said before, when you look at how you actually need to run this, it can be really kind of confusing. When I see that first time, I was like, whoa, how am I going to get that? But I mean, you kind of need to practice that. It kind of makes sense after a while. You are going to use some of the aggregation functions in the select. You are going to have many node and edge tables, so you need to kind of tag which one you are going to use for the arbitrary. And at the end, you are going to say, okay, am I going to try to find this shortest path for forever until the end of the data I have? So it's going to go and try to find it at the end of the table. Or you're going to say, you know what, I want to try only, I want to hook maybe 3 times or 4 times, so you can actually specify that. So if you look at that in a little bit details, that's what it's going to look like. So your graph path aggregation function can be any of those functions here. And your order clause is you're gonna tell that this aggregated function is gonna get grouped by, and we are gonna have many node and edge tables. Whichever the first one is not gonna be, because that's where you're gonna start from, so you don't really care about aggregation on that. So, but the rest of them probably you're gonna use the for path, and shortest path is gonna be in your match clause, and you're gonna pass the graph search pattern to shortest path. And this one here, as I said before, this one kind of controls the hooks between the entities. And if you just leave it as plus, that means it will try to find the data and until this kind of data. Or you can say that I'm going to repeat this pattern. I'm going to start from 1 time. You can say, okay, I'm going to jump maybe 3 times. If the data is there, that's great. If it doesn't there, well, it will return. So it's pretty complex, and it's not really easy to explain, honestly. So let's have some demos, and I will actually try to, I guess, summarize what I have been talking about graph database in this demo. So let me share my screen with SSMS here. All right. So we are going to start from the basics. And let's start from creating the tables, right? So what I'm doing here is I am creating users table, and to make that entity table, I'm just saying as node. As you can see, I have just a couple of columns there. And I have products table. As you might guess, that is a as node table too. And well, let's create them first before we go and do more. Okay, so I have 2 tables. Those are my entity tables. Now, I'm going to create an elike product, just like the example I showed you. And this is going to have only one created date column in it. Then I say before, index is important. So I'm creating the index on my from ID and to ID in this table. Then I'm creating a wish table, which is going to be just have the relation between probably the users and product. And let's put an index on it too. And that's it. So I have my structure. Now I am ready to actually put some data in the structure. So in here, I'm just using the insert statement. I'm just passing the column names and pushing some data in my products table. Then we put some data in our users table. And now we are ready to actually create relations. So in here, for example, I am creating a relation between product 1 and 2. I'm saying product 1 is like product 2. So this is the more, I guess, complex part, and many devs has issues with this because, well, none of the ORMs are actually supporting this. So you kind of need to do this manually, and you need to actually write and find this node IDs and kind of join them together. So if you're a dev, unfortunately, there's no ORM out there right now supporting this. So you have to do this still with the T-SQL, and you have to find to do that. So let's insert all this in our table. And same here, I'm actually going from product to product. As you can see, it doesn't have to be the same entity. For the wished, I'm going from users entity to product table. This, wish table doesn't care for entities. So let's run this. So I have the data in my tables. Now let's look at what my actual table look like. As I said before, you can see the JSON documents in them. And really, we really have no business kind of like with this because we are not going to use them. They are there. Now, I'm going to run the match. And as you can see, I'm going from product table to find the products. And I'm looking on the product ID 1. So this is going to give me all the information, right? It looks like I'm just getting the relation to information. So let's say all here. And now it looks like I have one item here. I have Kindle Fire 7, and it's $30. And retail price, I'm selling it for $50. But guess what? I have another product out there named Kindle Fire HD8, and I can offer this to my consumer because I feel like they are like each other. So it's pretty easy. A query I can run and return this data very easily. As you can see here, I can update the credit date, but I cannot update anything else. So this should work fine. But if we try to update any of the node IDs, age IDs, from ID to ID, that's not gonna work. So far, I have my structure, I have my data, and now let's see some more examples. So this one, we just see it. This one returns the like products. And if you want to actually make this more complex, we can do that. But as you can see, now I have many entity tables. I have users table, product table, and I'm going another product table. And I'm using 2 relation table. So my match looks like I'm going from users to product table by using the wish. So this is going to give me the wish list. And just pay attention to, I guess, the arrow here. That's where I'm going. But I'm not stopping out there. I am saying, okay, I want to see the wish list, but in the meantime, I want to see all the products in the wish list if I have other products like them. So, and I just care about the user ID one. You can write the same thing in this way. You can use the AND if you like, and it's going to return the same data. So if I run this one, what this is going to find is it looks like Anna wished Kindle Fire HD8 in this date, and I can offer her this product because I have it in inventory. Same with she has iPad 3, I have iPad 2. So things can get more complex here, but still, I think it's pretty easy to find what we are looking for here. All right, so let's see what is next. Now, let's get a little bit more complex. Now, everything I talked about was just the graph database tables. Graph database tables can be joined by any other tables. That makes them more useful, more flexible. You can use them in SSIS, it's just like regular tables. You can run this query for SSIS, everything. So in here, I'm going to try to actually introduce some more tables and try to create some kind of like a smart, I guess, a model. In my model, let's say I am a company, just like Amazon. I have products and I have many warehouses. So I keep those products in many places. So I have users who actually buys the product. So what I'm trying to do here is, well, if this person is buying the product, I want to send the product to that user wherever is the closest to warehouse, right? So I don't want to send the product from very far away because probably I'm the one maybe paying for the shipping. And I want to be sure that I'm paying less for shipping. So that's what I'm trying to solve here with graph tables, the database tables. So the first thing I need products. That's my entity tables. I need a warehouse. And what I'm using here in the warehouses is the geography, which is the geospatial data type of SQL Server. So this location is going to be really the latitude and longitude of my warehouse. So I'm going to create this, and that's going to actually go in my node table. Then I need users. So same way I have the geospatial data here for my user. But I really don't need their exact latitude and longitude, right? If I know their zip code, if I know their city, that's really more than enough for me to find the latitude or longitude of the city or the zip code. I really don't need exactly where they live to actually come up with an estimate how much it's going to cost for me to ship. So probably that one is going to be maybe the city's latitude and longitude. So I'm going to do that here. Now, I'm going to create a table for in-stock. In-stock is going to be between my user and product. Whenever user is going to actually no longer. In-stock is going to be between my product and warehouse. So if my warehouse has the product, that's going to be a relationship between them. It's going to be in-stock. So I create that. And in process is going to be between my user and product. So whenever a user actually buys the product and payment is done, I'm going to create this relation, and then I'm going to know that this is in process. Now, let's put some data. So here's my product data, very simple. Then I have users. As you can see, this is how you actually create the geospatial data. I have the latitude and longitude. This is pretty easy to find. If you know, usually if this user is registered with you, you should know at least which city they live in. So you look at that. So you can even use the Google to actually find this. So I'm going to insert all this data to my users table. Then my warehouses. I know where my warehouses is. So it's going to be pretty easy to find this data for me. And they are not going to really change that much. So I'm going to actually put my warehouses too. Now I'm ready to make some relation between those entities. So what I'm doing here is I'm really saying which warehouse has what product. So I'm going to insert all this in stock relation. Let's see, in process. All right. Let's run that. Now I have in process. Now I'm ready. I have my data. So what I'm going to try to find here is I'm going to find all the in process products, and I'm going to try to find the distance between the user and my warehouses. So I have a subquery here. I'm going to run the subquery first, so we're going to talk about this first. So to understand the data here, looks like I have a user ID 5. His name is George. He lives in Virginia City, and he is buying a 27-inch monitor. And it looks like this 27-inch monitor does exist in 3 of my warehouses. One is in Minnesota, Dallas, and Seattle. The biggest, I guess, the calculation here is this one. This one is actually calculating the distance between my user and my warehouse. So it looks like George bought this, and it's going to be much cheaper for me probably to send this monitor to him from Minnesota because the miles is much lower. So that's why I'm using this window function here, and I'm just picking the priority. So in really the other query, it just picks the priority one. So it's going to only pick this one, that one, and whatever is one, really. So as you can see, that one is depending on the number of miles, and I want to send this product to my user. Which one is lower? So if I go and run the whole thing here, as you can see, I don't see all that extra data. Those are the places that I should send products. You can use it like that, or you can say that, you know what, let's say here 1200 is pretty high, so maybe I need another warehouse, or maybe I need to move this product to another warehouse which is closer to George if there's a lot of people are buying this product from Virginia Beach area. So that is pretty useful. All right, looks like we're in 45 minutes. I can show you one more demo, and that is for the shortest path. That was the last one I just powered for 2019. So in here, what I'm doing here is I am creating a people table, which is a node table, and I have friends. So what I'm going to try to do here is I'm going to actually figure out, so I'm going to give one user, and I'm going to see how many, I guess, hoops I need to jump to meet another person. So which is kind of complex. Let's actually run this first. So we have people table and friend relation. We put some people in it. Then I am saying which person is friend with which person. So that's all it really does in this insert statement. So I'm going to run that. So there are some relations. People know each other. That's all I did. Now I am actually ready to run this shortest path. So let's look at it. I'm going to still run the subquery first here, so it will be much easier to understand. As we can see, this is the first person. This is where I'm starting from, and that's the person ID one. So I don't really need anything extra on this. But now I'm going to actually use the string egg function, and I'm going to put this character between each person this person knows. And this is going to be a group path. And as you can see, I'm going to tag it as a path here. So if I run that, my shortest path is going from person to person by using the friend. And by putting the plus here, I'm just saying go as far as you can go. I don't really care how far. So if I run this, you're going to have this data here. So it looks like George knows Bob. And last node, which is the last value here, is the Bob. And also George knows Bob, and Bob knows Katie. So as you can see, it goes deeper and deeper. Now, this is everybody actually I can reach from George. Now, my other query actually goes and finds Lisa. So what I care is how can I reach Lisa here? What is the shortest path between George and Lisa? So as you can see, I'm just saying the Q last node is Lisa, and this will return me shortest path. It looks like to reach Lisa, George knows Bob, Bob knows Katie, Katie knows Mike, and Mike knows Lisa. So that is the shortest path I can actually reach Lisa if George wants to meet Lisa. This will change dynamically. So what I mean by that, let's actually introduce more relations to this friendship. So let's take this out, and I'm just creating more friendship between people here. So don't forget we have Bob, Katie, Mike, Lisa. So 1, 2, 3, 4. And if I introduce new ones, maybe George meet with somebody else, right? So I run this one, and I want to run the same query again. Now I'm looking for George and going to Lisa. That new relations that I just actually introduced, we had the 4 before. Now, actually, George knows Bob, and we introduced Pat. Pat knows Lisa. So actually, this is shortest path to reach Lisa in this case. So dynamically, this will find the shortest path between two entities easily. So this is pretty good with the data science, usually. All right, let's go back. So that was actually my demo, and thank you for joining me today. I enjoyed it, and thank you for inviting me too. And as I said before, I can answer any of your questions now, or you can ask me from LinkedIn or Twitter. I'm always there, and we'll check my blog too. And thank you again.
Thank you, Hasan. We have a couple of questions in the chat, if you can read, or may I help you?
Yes, I can read them. Let's see.
Okay.
Graph tables can be partitioned. I'm guessing so because I've never tried that before. They are just working like the other tables, but partition, I'm not sure. I don't want to say yes and no to that. And frameworks, I tried, but NodeID and HID, the entity framework has no idea what that is, and it cannot make the relations and the joins. So we kind of need to wait, I guess, to see. And Hibernate, I used it before, but I will be surprised because if entity framework doesn't kind of, I guess, handle that, I will be surprised and Hibernate does it because since this is a Microsoft product, I don't know. And second one, is there any approach for an end user to query any sort of graph database? I have in mind as an example what Tabular is to SQL relational tables. Any sort of graph database tables. So, Thomas, can you maybe explain that question a little bit better? So in the solutions right now, the only way that actually I can do this with just with, I'm not sure if that's what you're asking, but it's a store procedure, really. Because as I said before, ORM doesn't work, entity framework is not really there for it. So as a developer, this is a kind of like a challenge because they love to use ORMs. So they kind of need to use, T-SQL or the store procedures to insert data. And well, you can still write the select statement easily on the ORM. You can just convert it to an object, but especially you will have issues when it comes to insert relations to the relation tables.
Hello, Alan. This is Tomaro. I would like to try to clarify. The point is, set aside the construction of the graph database. I would just like to know if the user can query and extract data out of it, in the sense that someone creates and feeds this graph database, but the user is flexible in the, let's say, in the queries, in the way to extract data, in the way to link the entities together. While right now I have seen very specific cases due to the flexibility and the complexity of the system. So that's the topic.
Yeah, I mean, I guess the example I can give you, for example, a Stack Overflow database, right? I got that, I downloaded it, and I actually did all the structure myself. So I was able to create user and user nodes and questions and answers. So I had the ask relation between them. That was a challenge. It was not, and that was not like an easy, I guess, product. You really need to understand how the graph database works and come up with a nice model. And many people are actually kind of worried about what if, since it's still a new product, many people doesn't really believe in it when you have too much data in it, how is it going to actually handle? So there's still like those questions out there, some of the questions you ask out there, I don't really have an answer because I'm still kind of using it. And the, I guess, alternative to that, to graph database and SQL, you have the Cosmos DB Gremlin. So Gremlin has been out there for longer, but you're going to have the same kind of issues with the data modeling. And I'm not sure if I answered the question right, but those are in my head right now. You can always write me from the Twitter. We can talk about it.